Okay, so basically, or hopefully today, by the end of this lesson today, you should be done with your project. So other than the report, of course, like you'll be done with the third part, which is the model application. So let's start. Start. Okay, so before we like do like the model application, let's just go to your project and read your project. And because so like you go to your project file, groundwater, supply design. So this is on Canvas. You will find the same thing in Canvas. Let's see what we did. So we've already seen the hydrologic setting, like where that this is an unconfined aquifer that has a base at a certain height. I told you to set up a model that's 4.5 kilometer times 1.5 kilometer and to use a grid cell of 50 meter. I gave you like this data and you use this data like the resistivity data and the hydraulic conductivity data to create your hydraulic conductivity field. You defined like your boundary condition, like your river, like your recharge, and we also have a pumping well. We define this, but it's not pumping, like it's a pumping rate of 0. Now, we calibrated the model. So last time we noticed that our model has some difference at what we are observing in the field. So we want to improve this. So we did an automatic model calibration with BEST. And BEST basically improved your parameter estimate for your hydraulic conductivity to get a better match between what you are observing in the field and what your model is simulating. So and then like the last part of this, I don't know what this model development. Okay. So the last part of okay. So the last part of so like you calibrated the model, like the last part is like the model application. So let's lead like why did we why did we set up and calibrated this model? So it is planned to install a municipal water supply well halfway between observation well B10 and the river. So basically, we like look here. So this is observation well B10, and this is the river, and we are planning to put like a pumping well somewhere here between like these two. Okay. Let's go back to your project. Also, another thing, a new industrial area is planned in the study area as shown in figure 3, resulting in complete sealing of the surface. So like, in addition, there is like an industrial area is planned here. So let me show you like, let's just talk about the first part. So like the first part of your project is that like you have like an aquifer, put something like that's your water table. Okay, so like the water table looks like this. Okay, and for this water table, we will put like a pumping well. We put a pumping well somewhere here. We have like a pumping well. Which will be like pumping water out. Okay. And once we start like pumping, we already so like you have like a river somewhere here. Once we start the pumping, we already know that there will be like a go down. So like once we start pumping, like this is your ground water table. Yeah, and once you start pumping, what will happen? Like this groundwater table, like it will go down. So you're like so this is before pumping, after pumping, it might get your groundwater table will look something like this. So this is before pumping, this is after pumping. And we have learned it from before, like the distance between. So this is like your H node. So this is H node, this is prior pumping. This is like your H, like your head after pumping. And we know like the distance, like this distance here, this is called like drawdown, like S. Okay, so here, as you get like this is drawdown, and here like you get like drawdown. Okay? So basically, like we learned this before, that like drawdown, okay, is like your H node, like your head before pumping, minus like whatever head after pumping. So here, this is before pumping, this is the head would look like after pumping, and like this is the drawdown. Okay. So like your first part, like before we get to like the industrial area, like your first part of the project, I'm telling you how much water you can pump here from like this pumping well that we will install. So we will install like a pumping well. It will be like somewhere here. I'm telling you like how much pumping we can pump from this well, such that the drawdown in my 12 observation points. I have like here B1, B2, B3 until like B12 here. I have like 12 observation points. I want like the drawdown in the 12 observation point in all of them to be less than or like equal like 1 meters. I don't want this S between like my initial water level and like my final water level after pumping to be below this regulatory limit of like 1 meter. Okay, so basically that is like the first question like I'm asking you. Okay, let's go here to your project. It's your project. So let's go here to your project. For each of the following scenario, what is the maximum rate of water that can be pumped if the drawdown of the water table should not exceed like 1 meter at any of the observation? Okay, so scenario 1. So that's like you have to do 3 cases. So scenario 1 is like the pre-development condition. Pre-development condition means without having this industrial area. So like here, like I have to, that's like, let me show you, like that's like scenario 1. Here, that would be scenario 1. You have like recharge here, like over your whole site. Recharge over like, that's a recharge over your whole site. That's 0.008 meter per day. Okay, that's like the recharge everywhere. So here, that's like your pumping well is here. That's where you are pumping from. You like recharge like 0.0008 meter per day. So that's like your scenario 1 here. That's like scenario 1. And I'm asking you, what is the maximum Q here? What is like the Q maximum? What's the maximum Q that you can pump from here, such that like the drawdown in all the observation well is not going to exceed 1 meter. Okay, that's like scenario 1. Now in scenario 2, I'm asking you, like, so that's scenario 1. Like scenario 2, I will tell you, like, it's the same thing. That's like same things that you have here. Okay. The recharge over like your whole area is again 0.0008 like meter per day. Here is your pumping well, but now we will do something else. There will be like an industrial area here. So we will put like an industrial area such that this industrial area will seal the surface, and when this like industrial area is like totally like it's like impervious. So for example, like we'll have like a curve number, for example, like you remember this from like 90, so like a perfect, like it will seal the surface. So if I have like an industrial area here with like impervious surface, what will happen to the recharge over this area? Anybody tell me? Huh? Lower to what? Zero. To zero, right? Because basically, like any water that's like happening here, it will not infiltrate, right? Because like remember, like when you have like a curve number like this, like very high curve number, then basically water does not infiltrate, right? So basically, like so what will happen to this water? So like basically the water over the industrial area, what will happen to it is that you will collect this water and drain it through your storm drainage system. It's not going to infiltrate in the subsurface. So basically, in that case, the recharge here, recharge here would be like equal to zero. Okay. So you'll have like two recharge zones. So you have like everywhere in your model domain, you have like this recharge, and I told you this recharge is very realistic here for Florida, for example. And then in this industrial area where you are planning, the recharge here would be like zero. And again, I'm asking you, what is the, like with this new recharge, what will be like the Q maximum? Again, the maximum amount of water that you can extract from this well, from the pumping well, such that in all the observation well drawdown again will be less than or equal to 1 meter. Okay, so that's like scenario 2, where you have like the development. Now we have scenario 3. That's like scenario 3. And like scenario 3, like we will expand on this like projects. Like your next project would be all about like this scenario, which we will develop here, which I'll show you here. Scenario 3 is that, again, this is like a recharge here is equal to 0.0008 meter per day. The pumping well is here. Again, it's the same problem, like what is like the Q max. But I'm telling you that in this industrial area, like we have an industrial area, make it a little bit bigger so that I can write more details. Again, it's like the same industrial area. We have like the same industrial area. But I'm telling you, so this is the industrial area. I'm telling you, like in this industrial area, we're gonna do 2 mitigation measures. So like the first mitigation measure, like we're gonna do 2 mitigation measures in order to reduce like this like impact. Okay. The first mitigation measure is that I will create like the pavement here, like my land, use land cover. It's not going to be totally impervious. I will create some pervious pavement. So basically, remember, like I gave you one article, like in your homework 6 to read about like nature-based solution, low development infrastructure. So basically, that's what we will do in project 3. So in project 3, we will be studying more of this like nature-based solution. Basically, you'll have a case exactly similar to this, but instead of having an industrial area, it will be like a residential area, which will reduce recharge. And then I will tell you, design and propose some nature-based solution in order to increase like infiltration and accordingly increase the recharge. So here, like for that case, two nature-based solutions are proposed. The first nature-based solution is impervious pavement. So like we're gonna use an impervious pavement, and like that solution, if we use that impervious pavement, that could reduce about like 30% of that initial recharge. Okay, so if we did this impervious pavement, we can get about like 30% of this number. So basically, the recharge here, instead of being like 0, it would be like 30% of this value, like which I have it here calculated as Yeah, just 30% of this number. Like if you got 30% of this number, then that will be something like this. So recharge here, recharge will be equal to 0.00024 meter. So that's like the first like nature-based solutions that's proposed, is like instead of making like this area completely sealed, like allow do some technology in your pavement design and whatever, and like some green areas or whatever, so that you will increase you will get about like 30% of the original recharge. Now that's one of the solutions. In addition to this solution, we're going to implement like two of them. Like the second nature-based solutions that we will implement, and that would be like the main topic of your project 3, is infiltration bond. Like we want to create some infiltration bond here. So this is like the industrial area, and we will like here, I will like create like an infiltration bond here. Okay. And basically like how to create like, so basically like I will take like, there will be like some direct runoff, like excess rainfall here, and instead of like this excess rainfall or direct runoff, and instead of routing this excess rainfall to my storm drainage system, I will route it to some like infiltration bond here. Okay, so I will route it to like some infiltration bonds here, and instead of routing it to the storm drainage system. And that's what you will be doing in project 3. So basically in project 3, you will be you will be designing like these bonds, this infiltration bonds, so or routing like direct runoff or excess rain. Okay, and this infiltration bonds are capable, like this infiltration bonds are capable of reproducing about like 50% of like the original recharge. So the recharge here like will be about like 50% of like the original recharge over your industrial area. So remember, like that is 50% over this number. So like my recharge here is like 0.08, like 50% of it like 0.0004. Okay, so like this, that's like 50%, like half of this number. But now like this area is smaller than this area, so I just need to see like, so if I would put here like the recharge rate here would be like 0.0004, but if I put it over like a smaller area, then it would be like a larger number. So basically like to see like the actual recharge here, basically like multiply this number, like you get the total volume of recharge, and then you divide it by this area. Like let me show you, like give you an example. Let me, or let's do this calculation. So basically, like I have here, for example, like this point. So like this point here, for example, the coordinate of this point here is like 600, and like the y coordinate is like 200, and like the coordinate of this point here is 200 and like 700. That's the coordinate of this point. The coordinate of this point here is so they just want like the coordinate of this point here is like 150 and 750. That's like the coordinate of this point. And similarly here. So here, like the coordinate of this point here, for example, if you look at the coordinate of this point, that would be like 2400 and like 200. So basically, like from these coordinates, I can calculate like the area here, and I know like I get like 50% of the recharge, then I could ratio it to like the area. I mean, let's do it. We can do it. So basically, So like from here, like, so basically to get the area, you need to get like this distances. So like, so from here to here, like this distance here, that would be like something like this, right?
Yeah.
And then like from here to here, that would be what? That would be 550. Yeah. Yeah, that would be 550. Okay. So basically now I have like 50% because I will not like 50% of like this recharge would be over this area. So let's see the volume of recharge. You can calculate like the volume of recharge. That is like recharge, like the volume of recharge, and that would be like 500 like meter, like 800 like meter time, like 50% of this guy. So that would be like 0.0004 meter per day. Okay. So if you did like, you did this calculation, I got like it. What number? Like, can you do this calculation? What number do you get?
396.
Okay, 396 meter cube per day. Okay. So now, like, this is like 396 falling, like recharging from this area. Now, they would be like redistributed over this small area. So basically, like recharge over like this area, like recharge. This is volume here, okay? Recharge over like the bond. That would be like this number divided by the area here. So that would be like 396 meter cube per day divided by this area here. So like from here to here, that's like 50. So like this from here to here, that's like 50. And from here to here, that's 550. Okay. So that is divided by like 50 meter times 550 meter. And can anybody do this and tell me what number you got?
0.0144.
0.014 meter per day. Okay. So basically, the recharge here in this area, so like the recharge here is like 30% of this one, and the recharge here is 50% of this one, but like it's distributed over like a small area. So let me delete these. Let me keep it. That's okay. So like recharge here in this area, that would be like 0.0144 meter per day. Okay. So, which is like 30% of like recharge over like 0.8 over like this water. Okay, is this clear for everyone or no? Yes? Like, is this clear what I'm doing here or no? Yes? Yes? For everyone? Okay. So now, again, like when we do this mitigation, we were not able to claim like to recover like 100% of this 0.8. We only recovered like 30% here and like 50% here. We recovered 80%. Okay. Which means that like the Q here would be like less, right? The maximum amount, like so here, like Q maximum would be like so basically like I was able to recover like 30%. So I have two, let me repeat again. I have two nature-based solutions. One nature-based solution is not to make this area completely sealed, but to allow for some infiltration to occur. And so that could create about like 30% of this number. I have another proposal, which is to connect the direct runoff and let it routed to this infiltration pond, and that could create about like 50% of this recharge. Okay, that's like the two solution. So like if you added like 30% plus 50%, that's like about 80% of this recharge I was able to get it by this using. Okay, so now like in this class, basically we will see, like we will look at this problem. We will see now without like any development, if there is a community here, how much this community can pump without exceeding this regulatory limit. But then, if suddenly now this community, somebody like few kilometers, like couple of kilometers away, did something, like did an industrial area or a residential area or whatever, how this community will be like impacted, because like the drawdown, instead of being like below 1 meter, it would change drastically. So they will tell them, or reduce your pumping because you are now violating this like regulatory limit. And then we will see like if this was done with this mitigation measure, this would have like reduced like this effect. So that's basically what we will do today, and that will be like your what you will do in your project. So let's read this here. So now like you like you set up your model, you calibrated your model, and now you're ready to use your model. Okay, so here this is like just what I told you. Like this is scenario 1 without the industrial area. This is scenario 2 with the industrial area, and this is scenario 3 with the industrial area and like this mitigation. Okay. So here recharge 0.8 everywhere. Here recharge 0.8 everywhere except the industrial area, and here recharge 0.8 everywhere except in the industrial area. You will get like 30% of this number, and we add an additional pond area that will do another, like will mitigate another 50% over this area we routed here. Okay. So now let's go here. So like basically what I'm telling you for like for your I'm here telling you like for each scenario for your project, I want you to show like the hydraulic head, like how the hydraulic head change with each pumping scenario for this. And but also like I'm asking you here to for another thing, like if you read here like this part here, express your maximum permissible pumping rate, like the maximum Q here. So let's just say that, okay, let's say that like the Q maximum here, okay, is like 300 meter cube per day. Okay, let's say just that's like the maximum amount of water, so we can pump like 3,000 meter cube per day without violating this regulatory limit. Now I'm telling you to express this number not in meter cube per day, but in million gallon per day. I mean, why this is important? Like, why am I asking you to express it like your final answer, not like like once you read the final answer? Why am I asking you to express it in million gallon per day? Yeah, so that's a good answer. So that's part of the answer. Yeah, like the reasons that I'm asking you is like most of like the regulatory agency or people like who will be working in like the water resources sectors here, like the units that they are familiar with, like you go to state agency or water company or whatever, like the units that they would be familiar with is not like meter cube per day, but million gallon per day. So if you told them like I'm pumping 3,000 meter cube per day, they will look at you and tell you what's this. But if you express it as like, okay, I'm pumping like 0.5 million gallon per day, then they will know what you're talking about. Okay. So basically, million gallon per day, this is the unit that is more common in like in this part of the world than like meter cube per day. And as Juliana said, it's also because similarly, like this state agency in their report, they will express like the human needs, the amount of water per capita, our like water consumption. They will also express it in like million gallon per day. And this is like another thing I'm asking you in your report, like based on this Q, like the amount of water that you will say, okay, we can extract the maximum of this amount. I want you to show me how many people this new well can supply. So basically, in order to know this, you know, you have like, this is the total amount, and then you see the per capita need or per capita consumption. And then if you divide this total amount by the per capita daily water use, then you will see, you get a rough estimate of how many people could be supported by this new development. And why am I asking you to do this? Yeah. No, I'm asking you to do this because I want you to dig into these reports. Like, because for example, like, do you know what is the per capita water rate in like Lee County, for example? No. And you're gonna check, like, to find this information, you will have to dig on the internet until you get, for example, like South Florida Water Management District. Each year they will like produce a report and tell you like each county what is the daily water consumption like per capita or daily water need per capita. So basically, I want you to search on the internet, like find this report and like get this number so that you become familiar with it. Okay. So that if you later work in this sector, you'll be familiar, like, okay, if I need to know what is the daily water need or daily water consumption in Lee County, this is the report where I can get this number. Okay. So basically, and that would be from like South Florida Water Management District. So you'll find the report, and in this report, they will tell you the per capita water need or water consumption. I think like I think the last report that they have like 2022, right? Because like 2023, we are still in 2023, so that one is not ready. Yes. Okay, so I think that and then like one last thing in your projects that I will also, I mean, we will get to this when we reach this point. Like, is that like I will also tell you based on like, I mean, let's get like, or let me say it now, and we will look at this point in details when we do it. I'm telling you, like, is this a good location? Like, so this is the proposed area of the infiltration, like of the pond. Like, I'm telling you, based on your result, is this a good location, or could you propose like a better location for this one? And we will see this once we run our model. We will see if this is a good location, or can we find like a better location for this area. Okay. So do you have any question before we start about your project 3? Any question? Is this clear for everyone? Yes? Yes? I think once we start doing it, it will become more clear. So let's just start doing it, okay? So let's just come here. And so like, I think last time we stopped here. You have like a model, like we calibrated the model. So if you open like the calibrated model, for example, something that looks like this. So this is like the calibrated model. Let's run it, for example. Run this one. I don't know, sometimes MODFLOW. I mean, if you have MODFLOW installed on your computers, you're not gonna be that slow, but sometimes it's just that slow. I don't know, maybe because I'm using it on apps anywhere, or because like using this like OneDrive. I don't know. Let me stop this and run it again. All right. So just open like while I'm doing this, you can open like your calibrated model, like the models that we just made. While we are doing this, like you can open the models that we calibrated last time and run it, make sure it's running without a problem. Okay. Yeah, run it again. Okay. I run this here. Save as. Okay, now it's running. Okay. So let's see here. Let's just refresh your memory of what we did last time. So last time we had like we set up the model, we calibrated the model, and when we calibrated the model, we want the difference between what we observed in the field and what our model simulated. Remember to be less than the calibration criteria. I wanted to be less than 0.53. meter. That is like the head observed minus like head simulated. The absolute value, I told you to make it less than or equal like 0.3 meter. So once when we calibrated the model, we all got something. So like you see here, this is like 0, 0, 0, 0 here. Here you got like about 12 centimeter. Here like this is 0, 0, 0, 0. And here you got about like 17 centimeter. Okay. So that's like a very good like calibration results. Here you got like 17, like so your largest error between what you simulated and you observed is here, which is about like 17 centimeter, 0.17 meter, okay, or 0.18 meter, whatever. Okay, so we run our model. Now let's start pumping. But before we start using this model, let me tell you something about like model muse and MODFLOW and all these things. So as you have already noticed, like the model muse and MODFLOW, model muse, this is just like a graphical user interface for so many programs that are mainly developed by the USGS. Okay, BEST is like another program that was developed by another university in Canada, for example. Okay, so all these tools, they just come from different sources. Okay, and like Model Muse is relatively like a new software, so it's still like developing. It still does not integrate all these tools, and it's a free software. It's a free software. So in like a Model Muse, basically you have to do like a lot of things. It's not like your workflow is not like fully automated. Some of things you have to do it like manually. Like you have to update it manually. Otherwise, it's not gonna it's not gonna function. Okay. Versus like if you, for example, like there are like commercial graphical user interface, like GMS, for example. So like for example, like this commercial graphical user interface, what's this commercial graphical user interface? They get all these different MODFLOW models. So again, MODFLOW, this is just a code that was developed by the USGS to solve this partial differential equation for you. Remember, like this partial equation, like the groundwater flow equation, which is a partial differential equation. So MODFLOW just solves this partial differential equation. And then you could have different graphical user interface if you want to input like the data like with a graphical user interface as we did here. Like for example, when I used MODFLOW before, I never used Model Muse because I would just enter this data with coding. Okay. But anyway, so here like this, there's like one manual step which we have to do is like we have to like update our like original model, like the ones that we didn't like the original model, the non-calibrated model with the calibration result. We have to do this manually for our scenario analysis. Okay, so how to do this? You can, so this is our calibrated model. We don't like we can like we just open your original models, the ones that's not calibrated without using PEST. That's why I told you save these two in two different folders. So this is like I will open now my original model. So now this is my original model without like using BEST. Okay. So this is the original model without using BEST. I will create like now I want to create, let's say this scenario. Okay. So I will save a copy of this one. So like you make like save as, okay. And try to create these things, each one in a new folder. Otherwise, like these things, when they run, they generate huge number of files and it would be a mess. So like the right way, the right procedure when we do this modeling is that each new model or each new run, we create a new folder for it. That's the right way of doing this. So you come here, I will create like a new folder and I will call it like model application scenario 1. Okay. So this is like model application scenario 1. I will open this one. Then I will save like my original model, like the ones that's not calibrated. I will save this. I will call it like model application, for example, scenario 1. Okay. So I will save it. So now you don't need this. Okay. So now if you look here, hide this one. Hide floating meter control. So let me hide this one. And like you see here, like now you see the name, like this model application folder, and this is model application underscore like scenario one. Let's run this model and make sure that it's running. So like you click save, and then it's running. So it seems it should be running. Now let's look at the calibration data. So you see here, like you will have, see this is, what's this? I think this is, actually this is a calibrated model of the original one. Let me do this again. So I think I screwed some. I think, I mean, I even screwed it up. Okay, that's okay. But anyway, let's go here, just like the model setup. Let's do this one. I mean, it doesn't matter. Let me just like, let me just. This is a calibrated model. I will just like I updated this. Let me just bring the original one, like whatever we have here. So I think that was like 20. Okay. For you, like, because I just like did like a mistake when I was copying and pasting them, but for you, just want to show you like the original one, and then I will show you how to update it. Okay. So that's like 150, for example. Okay. Just like okay here. So that's your original model. Let me run it. That's like the original model here. So you see, like here, for example, when I run the original model, you find like a big error. Like here, like in the previous one, it was 0. Here you got like about 70 centimeter or something. Okay. So like I will just take like my original model. So that's like my original model. I will take this like my original model here, like save as. Okay. And go here. Again, this is a non-calibrated model because the calibrated model, that was the calibration was done through like best, which is like a different thing. So it will not gonna run like it will, like if you run it, it will have some problems, like some errors in running it. So now I save this one. Let me run it. Let me run this one. Hopefully it should run fine. I run this one. Okay. I will run this one again. Like you see here, you have a big error. Okay. So now this is like, now this is my original model. I will just update it with the results that I got from best. So the results that I got from best, that would be like, let me open like the best one. That's like, so here, this is the results that I got from best. So this is the models that I got from best. And if you go here to model parameters, like manage parameters, this is like the new value. So let me write this value. I will just update this model with this new value. So here, let's say like K1, for example. Like K1, for example, is like 11.6. Just do this, like if you know, like if you while I'm doing it, you can also do it with me. Like K2, for example, like 32.8. K3 is 167.8, for example. Right? K4, that's like 90. K4 is that's like 64, 65. Yeah. That's like 65. And like K5, that is 7, like 3. Like K6, that is 195, for example. Okay. So this is like, this is again, what are these values? This is like my calibrate, like when I run test, my new model has this optimal value. And if I added this optimal value to my original, so I will like just, so here, this is the result from my calibrated model. Let me close this one now. I want to save this one. And let me now open my new ones that I created here. And this new ones, this is, again, let me show you the steps again. Let me delete this and show you the steps again. Okay. So like I will delete this one. Okay. I think because it could be open. Let me delete this one. I will again open like this one here. I hope I saved it with the new value, like the old values. If you go here, yeah, see, that's like my original model. That's like my original value. So I will like, now I want to use this. So I will create like save as, okay. I will go here, like this is my original model, like so. I will like create like here, model application, scenario 1, okay. I will give it like a name here, model application, like scenario 1, okay. I'll give it this name and then I will create save, okay. So now, like you see here, I have like model application scenario 1. So now, and like under this folder, now this is my original model, the non-calibrated model. I will update it now with this new values that I got from best, okay? Because if I use the best, like the models that I directly got from best, is not going to work. It will give you an error. Okay, so I will just update like, so this is my original value. I'll just update it with this value. So here, that would be 11.6, for example. This would be like 32.8. This would be like 106.7.8, for example. This would be like 65. This would be 733. And this would be like whatever, 195.5. Okay. Something like this. Okay. Then I will like click OK here. And then if I run this now, hopefully it should run fine. So let me run this one. So you see now it's running and it should now have like the new results. Like, so if you look at the error here, again, it's very small. Like this is 0, 0, 0. Here I got 11 centimeter, 0, 14 centimeter here, like all this 0, and I got 16 centimeter. Okay. So now I have my calibrated model, but I just updated it manually. Like I didn't, let me repeat again. I didn't use the one that was produced to me by best, because the ones that were produced to me by best, it will, like if I will use it again, like with MODFLOW, it's not gonna function. So basically, I like from this model that I got from best, like the calibrated value, I will just like see what are the new K value, and I will make a copy of my old model and then update these numbers. And then once you update these numbers, then it should work like this. Okay. So now I have a model. Okay. Now I have like the model for my scenario. Okay. So now let's do scenario 1. So basically, like this model will have like this recharge. It's a calibrated model because you see already like the error between what we are observing in the field and what we are simulating by our model is very small. So now I can, instead of doing this experiment in the field, I can do this experiment with my model. So let's do this experiment. Let me show you here. So here you should have something that's like a pumping well. If you click here, let me show you how to bring this. Like, so to bring this one, you can, if you come here, show, for example, all your object, then you will like select pumping well or whatever name you have here. So I think whatever name you gave it, like just select this object, then you click here, then you will have it. Then if you click on this red thing, that would be like the pumping well. So the name is pumping well. It could have a different name. This object could have a different name for you. the pumping rate is 0 because like I'm not pumping anything yet because I just added this as a dummy, but I was not using it. So now let's run this model and let's run this model one time. So I will run this model. Here, we'll run this model. Now, let me show you what we have here. So if I run this model, now you see here, this is like my simulated value, okay? So this is my simulated value, like at B1 without pumping. So let me write this down. Where should I write this down? Let me erase this and write this down, and we will see how this number, like how my head will change with pumping, okay? We will see how my head at B1 is changing with pumping, okay? So here, this is like the pumping. I will start pumping, and then I will see how the head, for example, is changing with pumping. So here, let me write this down, and so that we can observe how this number here is changing with pumping at P1. Okay. So let's say like so here, let's say like this is like Q, and this is like meter cube per day. And now here, that's like here, like this is my H node, like my head at node, and like I'm doing all this at B1. Okay, so at B1, my H node, like here, like this is my head before pumping, is like 107.5. Okay, 107.94. Okay. So this is my head like before pumping. And now I will start pumping, and then I will see like how this number here, like let's say I will start pumping 300 like meter cube per day, and then I will see like this my H node, this is my here. Point here. Here. I have like my pumping well is here. Okay. This is Q here, and like this number here, this is without pumping. Like here, when Q was equal to 0, like let's say this is my observation well here. Okay, so when Q was equal to 0, what I was observing here was like 107.94. Okay. Now, when Q, that's when Q is equal to 0. Now, when Q is equal to like when I'm pumping that much, then we know like when I pump here, then that will look something like this. Okay. So now I'm asking you what would be my new H. Okay. So that's like basically, so this is like here, this is like H node, and after pumping, I want to see what would be like my H here after pumping. And then the difference between these two, like the difference between like H node here, like H node and H, like this difference here, this is called like the drawdown. Okay. So the drawdown basically, you like your drawdown S is like H node minus H. Okay. That's like this. Your head prior to pumping and your head after pumping. So let's do this experiment. So prior to pumping, my H node, like this level, my initial water level was here at P1, just as this one. Now let's do the pumping and see how this will change. Okay. So now let's do the pumping. So like we come here and we go to pumping, and we make like the pumping rate. Let me show you like 3,000. So is this correct, or I did a mistake here? Can anybody tell me, is this like what I wrote here? Like, is this correct, or is there a mistake? Yes, exactly. I have to make this negative. Exactly. Why I have to make this negative? because like remember, like if we have like recharge, for example, like when we added the recharge, like we have a recharge of like 0.0008 per meter per day. That was a positive because like recharge is like a source term. It adds water to my system, but this is pumping. It's like it should be negative because this is like a sink term. It extracts water from my system. Okay. So like when I add recharge, it's positive. When I do pumping, it is negative. Unless I am using this as like an injection well. So if this is like an injection well, if I'm injecting water, because sometimes, for example, somebody will tell you, you know what, I will take this water, like this excess rainfall from here, and I will just inject it through some, instead of doing this infiltration pump, I will just inject it. If, for example, if this infiltration pumps are exceeding their capacity and they are no longer functioning, I will take additional water and just inject it to the subsurface. So if you are doing injections, then that could be positive. But like since now we are not doing injection, we are doing extraction, so that should be negative because now I'm pumping water out of my system. Okay. So I will like click OK, and then I will click close, and then I will run. Okay, and then I will run. Okay, now it's running. And now let's see our new H. Okay. So now you see here, my H node was 107.954. My H now, like with this pumping at B1, the H became, what did the H became? 102.6. Okay. 103. This is 103. Okay. So now, what is it? Now, what is my drawdown? Can anybody tell me what would be my drawdown? With this, like with this amount of pumping, with negative 3,000 meter cube per day, what is the drawdown at B3? At B1? 0.6. So is this okay, or can I pump more? I can pump more, right? Because remember, I told you like the regulatory limit is that H can be like less than or equal 1 liter, right? So basically, I got a drawdown of 0.6. This means that like let I can pump more. So let me pump, for example, let's try like you want 4,000 again, like my initial water level. That's the same. That's my pre-pumping level when pumping is 0. So here, this is here when Q equal to 0. Now this is like I have this one. So let's run this experiment and see like that much pumping will affect. Yeah.
Results shows that the observation they interact one. So you raise low and
Yeah, I know it will affect the other one. I'm just looking at one of them, and then we will look at the 12 of them. So right now, yes, what you're saying is true. Yeah, because it's like it could be more than one another observation, but let's just do them one by one, okay? So that you get the point, and then I will show you like how you can do for all of them. Okay. How you can make this check for all of them. Okay. So now let's get here. I'm just illustrating the point. Okay. So like now let's get here and raise this to 4,000. So I will like raise this to 4,000, and then I will click OK. And I will come here, I will run my model, click save, say yes. And then like we come here, and then let's see here. So now I got my new simulated value is like 107. So what is the drawdown? Like 0.9. Okay. So 0.9, like did I reach the regulatory limit or I can do more? I can do more. So let's do like 5,000. Again, like this number is the same. and let's do 5,000. Okay, so let me come here. Let me close this one, and let's go to the pumping well. Like 5,000. Click OK. Click close. Do this one. Run again. Okay, so I got like 106.8. Okay, now so what's the drawdown? 1.1, right? Now I have like a drawdown 1.1. So now I exceeded my regulatory limit. So that means that like the Q maximum, it is like somewhere between like these two, right? So like just for this observation, like, but we need, remember, like this need to be maintained for all of them. But just like if we are just looking at one observation well, then you're like you just try to find the value between these two, like trial and error. Okay, now, but the thing is, as what's your name? As Kevin said, we are not only interested in B1, we are interested in all of them. So I want to, like this regulatory limit is not only at B1, it's at all of them. So I need to maintain, to make sure that like this regulatory limit is met in all of them. So to do this, like we will just like make a little trick. So to do this, like in order to do this, we will make a little trick. The trick is I will replace here, like we don't need this anymore because our model was calibrated. So we don't need this anymore. I will replace, like, just pay attention because this is a trick. It's just a trick that we are doing. Like we don't need this anymore because our model is already calibrated. So this observation value are useless. I will replace this observation value with my H node, like my water, my head prior to pumping. So my head prior to pumping, which would be like H node. Let me erase this one. That's like H node, my head prior to pumping, for like B1, like until like B. So like this H node, I will like just put it here, right? So that would be my H node, and that would be my simulated value again. So now when I run the model with any Q, like with any Q, the difference that I will see here would be like this difference. Yes, do you agree? Like in my first column, I will put like this one, and this is what I'm simulating. Then if I run it, that difference here will not be the residual, but it will be like the drawdown. Do you agree or not? Yes? No, we're not flipping anything. Like, do we need this observation value anymore? Because like this is the heads that we observed in the field, right? We wanted this to calibrate our model, right? We don't need it, right? Your model, but what we will do, I will like this observation value, I will replace these values with my initial head prior to pumping with H node, okay? So that when I run the model again, this difference will be the drawdown. It's just a trick, okay? It's just like trick, okay? So let's do this, okay? So like in order to do this, let's get our S like H node. So H node, this is like when we do pumping is equal to 0. So I will like just come here. I will like set this pumping is equal to 0. Okay, so I will set the pumping is equal to 0. And then pause, and then like I run this model. If I set my pumping is equal to 0 and I run the model, okay. I run the model. Then what we are getting here, like this is my H node. So this is H node at so at B1, for example, H node is equal to like 100.7 I don't know, whatever, this is what, 107.94. Or whatever, okay? And so on and so on. Okay. So now, I will like replace, what I will do, I will like replace this value with this value, okay? So instead of having like here, that would be my H node, like this value. So how to do this? You can just copy here, you can come here, you can copy these guys. And then like you can just like in Excel, for example, you can open Excel. Okay. And like you can come here, you can do paste, okay? And then like you click, see this something here, you like use text import wizard, and then you click finish, and then you will have them all here, okay? So that's like the difference. We don't need this one. That's like the observation data. We don't need this one. And that here, this is our H node here. So this is here. This is like our H node. And here, this is our like observation well or whatever. Okay. So observation well. Okay, so this is basically, so basically what we have here is our H node, like head prior to pumping. And then we will, again, let me show you how to do this. You come here, you copy all these guys. You come here, oops, let me do it again. Come here, you copy all these guys like this. You do paste. It would be like this. You can go to data, for example, like data, and then you can select like here text to column, and then click finish, and then you will have it like this. Or that's like one way of doing it. Another way, you can come here and like click paste, and then click here, text imported wizard, and like click finish, okay? And like this is here, this is again our observation name. This is what we observed in the field. We don't need this. This is the difference between simulated and observed. We don't need this. Basically, this is what we need here, okay? So now we will like just open our project here, go to model, and go to manage head observation. Another way you can do is like you can delete this head observation and import a new file. I mean, this is like really up to you. You can do it any way you like. And then just paste these values here. Okay, but be careful, like when you paste this value, be careful, like this is just marked like in the, not in a numerical way, but in the computer way. So this is 1, 10, 11, 12, and then 2, 4, 3. So be careful, like when you paste them, just that you paste them correctly. So for example, like what I will do here, I will start from like B, for example, like 2 to B9, for example. So I will take start, copy this one, and then I will go here. Like this is like, and then I will click here and click paste. So now I pasted, makes this bigger. So I pasted from like B2 to B9, then like B10 to B12. Let me do this one. So B10 to B12. I will like copy these guys here. And then I will, like paste them here. And now like this is the last one. So this is the last one. I will just B1. I will copy this one here. And then I will like click paste here. Okay, so now I have, now my observed head, I just replaced it with my initial, with my static head, like the initial head prior. That's all I did. Okay. I mean, you can do this in any way you like. You can just import it, like delete these ones completely and import it as a new file, or you can just copy and paste it like this. Okay. So now we will click OK. Now, if we run this model, can anybody tell me, like when I run this model now? So remember, like here, like when you run this model, you get like a column that tells you this is your observation point. Okay. This is the observation well, and this is no, this is the observation well. This is the observation head. Like this is the head observed. and this is the head like simulated, and this is the difference. When I run this model, can anybody tell me what would be this difference? Should be zero, right? Because basically, I just brought this guy here. Okay, so basically, if I did this correct, if I did the copy and pasting correct, if I run this, it should be zero. Okay, so I run this guy. If I did the copying and pasting correct, then we come here, and then it's like zero. Okay, like I mean, this is just a minor, like probably I just did like a pasting error here, but like you see, everything is zero. Okay. If you want to make it like really zero, but anyway, so that's like zero. Okay. So now, like, let me show you again. Let me show you, like, explain to you what is happening here again. So now what I have here, like this value here, like what I have here, like this value here, this one is a little bit off. Let me copy and paste this one again, because it's a little bit off. So I did like some properly copying and pasting error. So let me come here and to manage head observation. Yeah, see here, I did a copying and pasting error here. Let's do it correctly, okay? It's good to do it correctly. So let me copy this one. And then we paste it here. Yeah, so this is now correct. This looks correct to me. I click OK. Let's run it again and hopefully get like everything zero. Again, if everything is not zero, this means you did a copy and paste error. Like if you are importing it, you imported it incorrectly. Oops. While for this one, I'm like getting these weird values. This is the simulated value. This is the observed value. A little bit weird. Let me do it again. I don't know. There's maybe a ghost in my computer or something. Yeah, this one does not want to update. Let me do it this one again. Okay. So I do come here. I copy like this one. Do correct. Okay. I copy like this one here. Yeah, that should be correct, right? Let me check my self value. Yeah, that's 17942. Yeah, that looks correct. So now, like, hopefully this time it will be correct. Let me see again, like, if it changed or not. Head observation. Yeah, see, like it. I don't know, like it does not want to update this one. I really don't know why. It's weird. Like even like when you click OK, I clicked OK, but I don't know why this value is not updating. So let me copy here. Okay. Paste here. But anyway, it's like if it's a small difference, it's not gonna make a big difference because like this is, yeah, like you see here. Let me do it again. Control V. Paste. Okay. Oops. I screwed up this one. So now this one is working, but B10 got screwed up. Let me do this one again. So B10 here. Okay, so hopefully this is working. Yeah, okay, so click OK. Let me close this one. Let me check it for one more time. Head observation. Yeah, so now this looks, oops, no. Oh my God, I don't know what's happening here. Might have been easier just to like delete it and upload it again. I don't really know why this is not pasting correctly. But anyway, you can come here. Okay. Just copying and pasting. Click, click OK. Maybe click save. I don't know. Click save. But anyway, as long as they are like, as long as they are close enough, that should be okay. Yeah, like I got this one got screwed. Like this one got fixed, but I think my computer has a ghost in it. Like, is anybody getting this weird problem or it's only me? Yeah, like so B10. Yeah, like I don't know why. Maybe I really don't know why this is like this copying and pasting here is not working. But even like that's not a problem. Like if copying and pasting is not working, what you can do, you can just like delete this one and import them again. Maybe do this one more time. So here we get like this. We copy this one, delete this one. Okay. Yeah, I mean, I don't know if it didn't work this time. What? It's, oops. Still. I will do it one more time. If it didn't work, I will just like delete them and import it again. Okay. Import like these ones again. Like head observation. Let me enter it by hand. Maybe if I enter it by hand. 102.5216. 102.5. 216. Okay. So you click OK. I don't have to run because if it didn't update, it was not going to update here. Okay, so now at least like by hand it's okay. Now it's working. Okay, so let's do this. Okay, so now we have this one here. And see here we got like everything is zero, like this, like close enough to zero. Okay. So now we have like get everything zero. This is like close enough to zero, so that's fine. So now so now this is our H node. So this is our H node. Now let's see when we start pumping, what will be calculated will be just like what you will see in the difference. That would be the drawdown. So let's go here. Let's do like pumping. So like we go here, we come here like to the pumping, and let's do our like negative like 3000 like Q. Like let's do this one, close, and then we run our model. If we run our model, that will give us like the drawdown directly. Okay. Now here, so you see here, like you see here, we got like the drawdown. So like the difference, because now this is the observed, like please pay attention. Like this is the observed, which is like our H node, because that's like without pumping, our initial surface without pumping. This is now what our model is simulating with this pumping of Q is equal to like negative 300 like meter cube per day. And now, like you see, with this pumping rate, like my drawdown is almost like you see here, for example, like this is 1.005. Like you can, this is okay. Like I mean, this like because remember, like it does like like here with this thing with one significant digit. So here, like this answer, because like you can just consider this to be one, okay? Like you just like or yeah. So here basically, if you want to decrease it a little bit, like make it like 2.9 again this meter cube per day. You want to reduce it again, but this answer is like good enough, okay? So basically, like you see here, like your drawdown in all like the pumping well is about like almost like 1 meter. So this is fine. So this means that like Q maximum for this case, for the pre-development case, is about negative 3,000 meter cube per day. That's like the Q maximum for like the pre-development case. Again, this is this case. Like again, what is this case? This case, we have like this amount of recharge, and we want to see how much water you can pump from here, such that the drawdown in all the observation wells should be like equal to less than or equal to 1. So here we got like less than or equal to 1, like slightly larger than 1, but just like slight difference. Okay. Because you also have like some, remember, like you also have an error in your head observation. Like what your model is producing is not exactly what you are measuring in the field. Plus, you also have an error in what you are measuring in the field, right? Yes or no? Like, is this field measurement accurate or no? Like, for example, if I got like this table, like 5 of them, and I ask each one to measure like the head, I'll get 5 different numbers because there's a measurement error. So basically, so you have an error from your measurement, you have an error from like your model. So this is like a good. So here, so we already answered scenario 1 in your question in your homework. So scenario 1 Q maximum is like 3,000 like meter cube per day. Okay. And like how are you gonna comment on this in your report? So in your report, you will say I could pump like that much amount of water. The maximum drawdown I got was at B10. So let's see where is that. So the maximum drawdown that I got was at B10. And that is what is expected, right? Because like B10 is here, your pumping well is, or let's just look at our model itself. It's better. Why are we looking here? So here, this is B10. Let me make it bigger. Let me make this bigger. Okay. Let me even change this color, make it red or whatever. Okay. Let's maybe offset it also like 30. Okay. So that is not surprising. Like I'm pumping from here. I got like my maximum drawdown like at B10. Where else? Where is the maximum drawdown that I got? Not surprising at all. I got like at B8, B9, and B10. So this is like this is B8 here. This is B8, B9, and B10. So it's not surprising that where like the maximum drawdown occur like close to the pumping well. Okay. So that is what we got from this like case. Now let's take a break, like 10-minute break or something, and then we will see now if we added this recharge area are we gonna get like this same like obvious result, or like the whole game will change and the whole management of this area will just get screwed up? Okay. Let me highlight this one. So let's take a break. Let's get back maybe like 2:35. Yeah, let's get back at like 35. And we will look at this case and see how like the whole game could change with this industrial area. I have extra copies of these. Does anybody need like does not have one of these? Yeah, because like you can follow up with the test. Yeah. Does anybody need extra copy? I have extra copy. Oh, this one is messing you, and that's tell you. You want to get rid of this guy? How many warning messages about? This one is telling you. This page is telling you. As long as you wake up over the school minutes, yeah, that's all we care. Because this is nice, like basically like this part of the agreement. You can for example, other That is. Basically, just like
That's fine.
this is.
Yeah. Yeah.
So you can only unlock it if you have the other. Lock all, you get to unlock all the keys. You know, if you want to do that, and they're always like a billion.
For some reason, even though I have it set to negative 3,000 for my pumping rate, it still tells me that there's zero difference in.
Oh, because see here, this should be direct. Okay, later.
Okay. Then, was there anything else I needed to
No.
change or?
No, like you
That's
see
it.
here, yeah, that's it. Like you see here. That's like,
If I run this,
see, that should be pumping rate direct.
okay.
Because you're like calculated it, you're calculating it over.
And if I run that.
Yeah.
That's still giving me zero difference in head value.
This is zero difference in head value.
Yeah.
Did you add the pumping?
Yeah, that was the pump there, right?
I think I know why. Because. Yeah, you see this import. This is what I was telling you at the beginning. This was not.
Okay, that
So you
makes
have to
sense.
go
So I have
to
to make a
your
new one.
original, because see, this is import. This no.
Yeah.
I
Okay.
told you all these tools are
Yeah,
not connected.
that makes sense. So I have to make a new pump. That makes sense. Thank you.
Yo,
That was.
Okay, let's get back to this and yeah. If you still like, yeah, like I think like as a class, I think we are already like ahead of schedule. So if you are still like having problem with for example, here I see he had a problem. He basically was using like the calibrated model instead of the original model. He also had another problem in running his model. He was like the pumping interpretation here. He was doing like calculated instead of direct. Like this needs to be direct, like not calculated. Like calculated basically means that you are like what we are doing. This is just a direct pumping rate, not the calculated. Okay. So we are ahead of class. Like if you prefer like a next class, like we do like a project day where you can like work over your project on the weekend, and then we like do this. Let me know if many of you have a problem. But I think most of you are doing okay, and most of you are at this point. Or otherwise, like I think from the first class, one group also had a similar problem, and after the class, they came to me and we sat in the office and we did it together, right? And Scott was us, yeah. Scott, yeah. So now let's get back to this one. So this one, it was kind of like if you look at this one, what we did here, that was a kind of like obvious. It's like it seems that like this was like a waste of time, because like are we doing all this so that you can tell me that the maximum drawdown that you're gonna get is here? Well, I already know this. Like without any model, I already like I can see like you recharge is uniform, you have a boundary. Like I already know that like I will get with like this like uniform recharge, and like the hydraulic conductivity here, like it's different, but I would generally expect that to have like the maximum drawdown near my pumping well. That's what I would be like expecting, and I can even calculate this from C's equation, like or C's equation. Like we had like an equation where we can like do a rough calc, not C's because it's like here we have like a river boundary. So if you use this equation, but at least you know the maximum drawdown will be here. But you cannot calculate it with C's because like you have a river boundary. But so what? I can come up with another equation that account for this river boundary, and then like the hydraulic conductivity is also heterogeneous. You can also fix this. But anyway, so that's what we got from this first case study. Like from our first scenario, we got to know that like the maximum drawdown, like I can get like a maximum of like 3,000 meter cube per day without causing like drawdown of like a 1 meter in all of them. Let's move to the second scenario here, which is when we add like when this industrial area start to like when we have like this industrial area. So to do this, like how can we do this? Again, you come here, file, like save this one first, like click save, make sure that you save it so that you don't waste your effort. And then like file, you can come like save as, and then we go here, and then we create a new folder. Again, this is like the standard modeling practice, is that like each scenario you make, you create like a new folder for it. This is just the standard practice, and this is like in this class, I'm not asking you to give me like these small models, but this is the standard practice that's used. Okay. Is that like for each run or each scenario, it should have like it should be like a new folder. Okay, new directory. Okay, so you save this one, click OK. Let's just hide like this guy here. So if you hide this guy here, like you see here, this is scenario 2. So now we have scenario 2. So now scenario 2, what we want to do in scenario 2 is that like we want to add this industrial area. So like in scenario 2, you will add this like industrial area here. And like if you go in whatever like these things that I gave you, yeah, if any of you wants, I still have 6 of them extra, right? If you don't have one of these, yeah, you can take one of these extra here. Okay. Okay, so now let's add the industrial area. Before we add the industrial area, let's just yeah. Does anybody need one more? Need one? Last two. You all have let's before we like now we have like scenario 2. Before we do this, let's just come here and like see our recharge. Let's plot our recharge. So you go to contour data. Like again, let me show you like if you want to come like you come here to like data visualization, you go to here, you go to boundary, MODFLOW recharge rate. So let's apply and close and close. So if we look at our recharge rate here, like look down here, like at this status bar here, it's like everything is 0.00. Okay, that's like everything. Now we want to create like an industrial area, like somewhere here, and this like industrial area somewhere here. It will like this industrial area somewhere here. It will have now a recharge rate of 0. Okay, so let's do this. So like you come here like to object, and again like if you look here in like page number 4, like 3.4, I'm giving you like the coordinate of this one. So we can come here, and I think it start like, and I'm already like drawing them here for you like 600 and 200. So you can just come here like to 600 and 200. Doesn't need to be exact because we can adjust this coordinate later. So like 600 and 200. Like see the coordinates are written here. Like if you go down the street, the screen here, this is where the coordinates is. So see here like I'm 600. Okay, 600 and 200 doesn't matter. Okay, let's just put it anywhere. Okay. And then it ends at like 25, 200, like 250, and like 400 or whatever. So now I created like an object, and like this object here, like this where it looks like. Let me now give it a name. I will call it like recharge, like industrial area. That's like the names that I will give it, recharge industrial area. Now we come here, like this is MODFLOW, like this is recharge, this is -1, and now my recharge in this area will be 0. And then I go to vertices, and then I adjust this to the real coordinates that I have. So the real coordinate here, I think this is like 600, and this is like 200. Like the way, let me show you like how these things are. So the way these points are, like you have 1 to 5, that's how it works. So like point 1, let me show you what these points are. Like so, like if your shape looks like this, okay, it starts from here. So this is like point number 1. This is point number 2. So it goes from 1 to 2. This is like point number 3. This is like point number 4. And then it goes from 4 to 5. This will be point number 5 here. Okay. Okay. So this is like 1. So 1 should have like the coordinate, like here, for example, like of like 600 and like 200. Okay. Something like this. And then like this is number 2. This is number 3. Okay. But you can also figure it out from here. Okay. So this is like 2.4, and this is like 200. Okay. And this is like 2.4. No, yeah, 2.4 kilometer. Yeah. And this is like, is it like 750? This is like 750. This is like 600. And this is like 700. This is like 750. And this is like 600. Like this should be similar to the first point, because, and this is this one. And if I click OK and make sure that like your recharge is 0, if I click OK, now you see here I have this object here exactly where I need it. Like so, this is like the object exactly where I need it. So I can hide this object now. So you can come here, hide selected object. And now this is like my new recharge. So my new recharge is like 0.8 here and like 0 here. So like if you look at the status bar at the bottom, like here, like just look here, 0 recharge, and here 0.0008 like recharge. Okay. So now I have defined like scenario 2, and let's see how much water. Let's see like the drawdown. Like remember with like scenario 1, like with scenario 1, like the maximum drawdown, like S max was like 1 meter, right? That's like for Q max of 300, I got like an S max of like 1 meter, okay, which is a regularity like limit, okay. I got like this. Let's see now for like this case, what would be like what is the Q max, okay. So let's see for like this 300, how many meter will I got? Like so if you go here to our pumping well, let me remove this, we don't need it. So like you go to recharge, like you create none here, you apply, you just like get a clean view. So now like with our pumping rate here was our pumping rate like negative 3,000. So for this, like for this case, for this 3,000 meter cube per day, we got a maximum of drawdown of 1 meter. Let's see for this case now what we will get, okay? So now we run this. This is like a new toy now that you can play with. Okay. So let's see now what is so now like you see here, the max, like now the drawdown went from 1 meter to 1.8 meter, okay? And like the maximum drawdown is not happening where like as in the previous case. So in the previous case, I had like the maximum drawdown like a B9. Let's put them together. So I got like B1. Oops, what's happening here? Like the maximum drawdown is happening at B1. And like, can you guess where is B1? That's here. So I got like, so this industrial area caused like the maximum drawdown to occur here. Okay. So now like the maximum drawdown is no longer occurring here. Like at B9, for example, I'm getting a drawdown, like it's big, it's still big, but like my maximum is at B1 and B2. Like my maximum is like happening here and happening here. So this is B1. Let me make this larger for you. It's like on here. A, let's set it by 30, for example. Okay, so this is B1, it's occurring like the maximum drawdown is like happening here. We close all these guys. It's like happening here, and it's happening at B3 also, like it's happening here. Actually, the maximum drawdown is happening here at B3. Okay, so that's like the maximum drawdown for this model. It's happening here. Offset like 16. Okay. It's red. Okay. Okay. This is like B3 here. And where else? I'm getting here also like B2. I'll just highlight like the 3 like largest drawdowns that I'm getting. Okay. So like here, like the 3 largest drawdowns that I'm getting are here. And then that would be like 616. Okay. So for the first case, without like this industrial area, I got the maximum drawdown like near the observation well where I'm expecting. But now with this industrial area, like the maximum drawdowns that I'm getting is like here. Okay. And basically, I cannot meet this like 1 meter regularity value in any of them. Like, so if you see like most of them, like I'm not like all of them is about 1 meter. Okay. And like one of them is like 2 meter. Okay. So basically, like if you live in this area, you will find like a 2 meter drawdown, and then you will think like I used before, like before that, like here was like the drawdown. Remember, the drawdown here was very small, like was 0.6, for example, and then I find like 1.4 meter drop in my water level. And what will come to my mind, I will say, oh, I have this drop in my water level because people who are pumping here, they start to pump more. And that's why my water, I am having this drawdown. But actually, no, like you are having this drawdown. The pumping here did not change. Whatever the people were doing here, they are still doing whatever they are still doing. But you are having like this difference, like this 1.5 meter difference in drawdown, just because of like this industrial area that was put here. That's the reason. And then if you have like a shallow pumping well, it might like go dry or something, and then you will say, and then you will go down there to these people down there and tell them, oh, you're pumping more. They will tell you no, and then maybe a regulatory agency will tell them, okay, now you need to reduce your pumping rate, and then they will say, why? I mean, you're not doing anything different. And then, but if you like took this class, then you might know, okay, maybe nothing really changed it, but what it changed it is like the land use and land cover changed it. Like somebody came here and did something, and that's why like the whole game changed it. Okay. But anyway, you can see like the maximum amount of water you can pump here, if any, without like violating this regularity limit of like 1 meter. Let's see this. Let's bring it first to zero. Like so to see the impact of this industrial area without any pumping, you just bring this to zero, just to see the impact of this industrial area. So like you bring this to zero, okay? No pumping, and then we close this, we run this one, we save. Okay. Without any pumping, let's just see the impact of this thing. So without any pumping, like if I'm not pumping anything, I'm already see like I'm causing like, this is how much drawdown that I'm already causing like away from the industrial area, and like near the industrial area, I am already causing a drawdown of like 1.1 meter. So basically, I'm already without any pumping. So basically, like in order to meet this regulatory limit for this condition, basically you can with like this industrial area in that thing. So one thing you can do, you can like negotiate to increase this limit from like 1 meter, for example, to 1.5 meter. And then maybe you can pump something, like you can agree, okay, we can like exchange like this number. Okay. Like for example, like when I was working in Hawaii, I was working with the state water regulator, and I was like telling them what is this. I was telling them similar thing. I was like develop like a model for like a Pearl Harbor aquifer. This is like the most utilized aquifer in that area. And I was telling them like they have different pumping well, and I was telling them this is the maximum you can pump from like every and each of these pumping well without violating your groundwater sustainability criteria. One of these criteria was drawdown. So like we define like different groundwater sustainability criteria. One of them was drawdown. Other was like certain amount of salt water intrusion, like different water groups and different water use being integrated, all this. But one of them was this. So basically, one thing you can negotiate is like how could you maybe relax this limit, okay? And that's like for any yes, like if you are like that's exactly what will happen. Like if you are applying for a permit to do like a pumping well, and you go like to the regulatory agency here, they will ask you, they will tell you, create a model, one of these models, and show how will this affect like your nearby pumping well, and how will this affect your nearby stream, like rivers or something. So something very similar, like the stages of the river. So you show this impact, they will review it, and then they will give you the permit, or they will tell you, no, like reduce your pumping rate. Something very similar to this. Okay, they will tell you like reduce your pumping. Okay, but this is not fun because now we cannot pump anything unless we relax this regulatory limit. But what we can do is that like we can tell like this industrial area why don't you, like the water, whatever water that you have here, like your excess runoff, like not excess runoff, your excess rainfall or like your direct runoff, instead of routing this to like the city, the storm drain system of the city, which is not like a smart idea because you need to build like a bigger one. Why don't you just like infiltrate it? Why don't you create this infiltration pond and let us recharge and recharge our groundwater? So that's like basically one thing you can do. If this industrial area is not even there, you can tell them you can even do more, because if this industrial area is there, they cannot, for example, demolish it and put like this pervious pavement. They're not going to do this. But what they can do, they can route this water and like through this like infiltration pond. If this area is not there, you can suggest more than one of these nature-based solutions. And this is what you're going to do for your project 3. Like for your project 3, it's not going to be an industrial area. It's going to be like a residential area. And again, this will change the amount of like direct runoff. And now your job will be to propose some of this nature-based solutions, of like this impervious pavement, like other things that you will learn in order to reduce like this numbers. Okay. And increase infiltration. And once you increase infiltration, you are directly increasing recharge, because more infiltration means more recharge. So now let's implement like these solutions, these two nature-based solutions, which is basically pervious pavement here and like this on here. So let's do this. So like now, like here, like for this, like in your report, for example, you will like this is with 0 pumping rate. You can just show like you cannot pump anything. Like in order to pump here, you can say if you want to get like some pumping, you have to change this regulatory limit to 1.5, for example, meter or like whatever. Okay, then you can get some pumping from this well. Okay, that's basically. So I need like to see this type of discussion in your report. Okay. Now let's go to the last one. We still have like 15 minutes. Let's go to the last part of like your project 3. So the last part of your project 3 is like this analysis, this mitigation measure. So let's see here. You can like again save your work. So you can save this one. And then like you can go like oops. Then like here save as. You can here scenario like 3. Oops. Got an error. Okay. Let's just like come here and call this like scenario 3. Okay. Click OK. No, like this is not updating. Okay, so now like you see here, this is like updating, like scenario 3, GPT. Okay. So now let's like just do like the final part. Let's just add the infiltration bond, and let's change the. So how to do this? Like first of all, let's show like you can keep this. Let's show the recharge areas. We have like one recharge area here. We have like one recharge area here. And that's like the infiltration bond is like here. Let's start from here. It's only one cell. So we can come here and you can like create something that looks like this. And then I can call it like recharge like bond area or whatever. Okay. And then I can select which feature is this. This is like a recharge feature. And I can like the multiplier, the recharge rate here. Remember, I can take this for you 0.011 0.0144. So 0.0144. Okay. So we create like this one. So before we do this, like you change the vertices. So the vertices are given here. This is like, I think, I think this is like it should goes like so. This goes from 240. No, oops. 240, and this the y here should be like 200. Yeah. This should be like I think 450, and like the y here is like 200, and this is 4. It's like it's only one cell. Like this is like I think 750. This point here, this would be this point here 400. This like 750, and this would be like this is my original point, which would be similar to this one here. Again, like this is how it goes. The first point would be like this corner, this corner. So basically, this corner is here is giving like this number, and this corner here is giving like this number. So this only one model set. So like if we click OK, then we have something like this. It looks like this. Then like now this one like here, this is our area here. Now this is no longer 0 because like there is some infiltration that's occurring here, and like the infiltration is like 30% of this number, which is 0.0024. So here, this is 0.00024. Okay. So we click OK, and then we close, and then let's plot this to make sure that everything is okay. So again, to plot this, you come here from like this guy here, and you come here, and you go to boundary, recharge, rate, apply, close. Now, if you look here, let's check, like just look at the bottom status, like 0.0008 here, 0.000024 here, and 0.0144 here. Okay, so now this is our mitigation measure. Again, like in this mitigation measure, we are not like bringing back like the whole like pre-development, like the 0.08. That's about 80% of it. So you would expect to pump like less water, but at least you expect to pump something. But and I will like I will show you like another point also. Okay, so let's remove this visualization. We don't need it. So we can come here. We can like click none. We can click apply. We can click close. Let's also hide like these ones. We don't need them. So we like hide selected object. We can hide selected object. We can hide like this one also, like hide selected object. Okay. So now we get back to our model here, and now we are ready to run like our last scenario. So like you can click save. Okay, so let's see with this scenario here. So you see here, like with this scenario, what we see here, like I'm not pumping anything. This is just like with respect to like the pre-development scenario. You get here, you get like again in this area, like in B1, B2, and B3, you are still getting like and B4, like you're like here, like in this area here. Where is this? Let me close this wording. So basically, oops, we were able to do some mitigation. So this looks better than what we got before. So like without any pumping, just due to this industrial area where not everything is infiltrating, like only 80% of the original recharge is occurring, you get like a drawdown here of about like 50 centimeter. And now my question to you, and then you can start like play with the queue to see like how much you can pump. Like, so we can see this. Let's play with the queue and see how much we can pump with to get like to the 1 meter like regulatory limit. But without pumping anything, I'm already getting like a drawdown of like half a meter just because of like the industrial area is blocking not the total recharge, but 20% of it. Okay, 20% of my recharge. So now let's do some pumping. and see like if we did here some pumping, let's see how much we can pump. So let's say if we pump it, for example, like 1,000. Okay, so if we can pump like 1,000, now we pump like 1,000 here, and then see like with pumping 1,000, we still didn't hit the regulatory limit, which means we can pump more. So let's do 2,000. Do like 2,000. Okay. Let's see if we're gonna get this to this regulatory limit. Still didn't get it, so we can like do more. Let's do 2.5 thousand. Okay. Okay. We got like 2.5 thousand, and then we run here. Okay. So yeah, like you see here, like this is 1.2, so maybe like at P3 here is like 1.2, so it could be I need to go like below, little bit below like 2.5 thousand, like maybe 2.2 or 2.3, but this is not important. Like now the important point, like you can do this on your own, like you can just play with this number until like, because and each model would be different, so this number would be different for all of us. But now I'm asking you, like as an engineer, okay, like now let me bring back like my infiltration area. So like now, as an engineer, this is my no boundary conditions. This is my recharge here, and this is my recharge here. Okay. So I have like, this is my this is my industrial zone, and this is my recharge area here. And like now, like the maximum drawdowns that I'm getting is like somewhere here. Like this is the maximum uh, uh, drawdown like that I'm getting. So my question to you is this like a good location? Like if I'm asking you, you are an engineer and you are reviewing this design, what will you say about like this location of like this recharge area? Yeah, it's far from the areas that's most impacted, right? So basically, like in this area, you have low hydraulic conductivity, and that's why this area is like most impacted, because here you have like really area of already low hydraulic conductivity, and your recharge area is away from here. So if you want to make a better design, if you want to design this better, you tell them you can keep whatever this, you don't need to change the pond design, but just change its location. Like maybe if you put this pond location somewhere here, for example, or if you put it somewhere here, that will reduce like this drawdown, and then you can pump more, like then like this regulatory limit of like 2.4 of like 1 meter or something. So you can just like make this you can play with it, because now you have like this tool, you can play with it. You will say, okay, now I will like change my recharge area and put it here. I mean, we can do it now. So let's change our recharge area and then like put it here. Okay. And let's say like, I think, let's see if this will make any difference. Okay. So you can like come here. And let's say like, is this like okay or no? Like you see now, much bigger difference. Like that, like your drawdown was 1.2. Now, like especially you like having this guy here was very bad. Now it's much better. Now you can even pop more than 2.5. So with this new location of like your recharge area, you can even pump more than 2.5 because you are not at the regulatory limit of 1 meter. So basically, now you have a tool that you can use it for like doing better engineering. So like basically now you say, okay, like instead of, if I just relocated this, that could solve like a problem. Okay. Based on your understanding of the subsurface and what's happening in the subsurface and how your head is changing with your hydraulic conductivity value. So basically now this is like a tool where you can use it for making your design. Okay. And again, like this, what I'm teaching you here now, this has not like like this modeling process, like how to set up a conceptual model, how to convert a conceptual model to a computational model, calibrate this model, and do the model application. This tool, this process is like would be in any application, like it's like the process itself, like not the details, but the process. That's like the process of any model-based design. And as I told you, like before, I used to work in a company, an engineering company that design like a power plants. I don't know, maybe I said this to the other section. I used to work for a design company that design like these power plants, and like designing this power plant, like this big 500, 750 megawatt combined cycle power plant. That's not like any design you have seen before, because like you have this huge turbine, a turbine with the size of this building, that you need, like for example, the settlement tolerance would be like a millimeter, because if you have settlement more than millimeter, all these pipes that are connected would break. So like in a typical design, like how many loads do you have? 5, right? Yes, the typical design, right? Typical like a concrete design. Like you have 5 load of gates, like live load, dead load, right? Wind left, wind right. Yes. Earthquake maybe. 5, yes. You know, in this case, like to design a raft, like the raft, like the foundation that this turbine will sit on. Do you know how many loads do you have? Or how many cases of loads you have? You have more than 120 cases of loading, and you have more than 130 types of loads. And this you cannot do with like what you learn in, you know, like with like you do like your French equations. You have like, for example, when I used to work in this office, I didn't design these power plants. I just designed. They will give me like slab, like design this slab. So I will go to my Excel sheet. I have like my French equation, all this thing. I put like the dimension, and then tell me this would be like the dimension, and this would be like upper. But for this, like for this foundation, they do this model. They create a model and they test all these cases just like the same way we are doing. So this, like, even if you are not like interested in water resources, you are interested in transportation, you are interested in this is not transferable skill, because like what you are learning here is how to make a model-based design. Like you create a model and then you do your design on this model. Okay, I think that's all I have for this modeling thing. If you have any problem with your models, please just I'm available now after this class, so please just come. Like I can help you in my office now, or you can just come at any time, and I will like see what problems you have, and we can solve it.